Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a fascinating survey paper from the Papers with Code Trending list. It's titled 3D Scene Generation, a Survey, published May 8, 2025. This paper provides a great systematic overview of how AI is creating entire 3D worlds, organizing methods into 4 main paradigms. It highlights how recent deep generative models, like generative adversarial networks, or GANs, where 2 neural networks essentially train each other, and 3D representations, like neural radiance fields, or NeRF, a way to learn a 3D scene as a function that can render new views, and 3D Gaussians, which represent scenes using many small, detailed 3D shapes, are really boosting the realism and variety of these environments. And speaking of resources, the authors have also put together a fantastic GitHub repository to accompany this survey. It's essentially an awesome list, which is a curated collection, in this case, of over 300 recent studies in 3D scene generation. They've included summaries and links, all neatly organized for easy browsing, if you want to dive deeper into specific papers. And this growth is really well illustrated in the first figure of the paper. It shows the annual statistics of publications in 3D scene generation. You can see a pretty dramatic rise, from just a handful of papers before 2018 to nearly 100 in 2024, with a strong start to 2025 already. This visual really underscores how quickly the field is evolving, with different generation methods also gaining traction over time. So the survey then breaks down these generation methods, and this next figure, figure 3, focuses on the first main paradigm, procedural generation. Procedural generation, well, it's essentially about using algorithms and predefined rules to create scenes, rather than an artist handcrafting everything. This figure shows 3 main approaches within that. First, rule-based methods take initial parameters and user interactions, then apply specific rules, like those based on fractals or formal grammars, to output the 3D scene. Second, optimization-based methods use parameters alongside constraints, which are specific conditions or requirements the scene must satisfy, to find an optimal layout before generating the final 3D representation. And third, there are LLM-based methods, where a large language model takes text input to either design a scene layout directly or generate code that then produces the 3D scene. Okay, so moving on from procedural methods, this next figure, figure 4, shifts our focus to what the paper calls neural 3D-based generation. These approaches typically employ 3D-aware generative architectures, and they often use some kind of intermediate representation to control the spatial arrangement of the final scene. The figure highlights 4 main ways this is done. First, in A, we see methods using scene parameters. Here, an input like text or an image goes to a parameter generator, which outputs specific attributes like 6D pose, that's the object's 3D position and orientation, and shape information, which then guides the creation of the 3D scene. Next, in B, there are methods based on scene graphs. A scene graph is a structured way to represent objects and their relationships in a scene, almost like a family tree for scene components. Text input is usually encoded into this scene graph, which is then decoded to produce the 3D scene. Then, C shows generation using semantic layouts. A semantic layout is essentially a map, either 2D or 3D, that outlines the structural and meaningful organization of a scene, like where the walls, floor, and furniture should be. This layout, or sometimes just text, feeds into a neural 3D generator. And finally, D illustrates the use of implicit layouts. Here, text or an image is encoded into a more abstract, often feature-based representation of the spatial structure, which is then decoded to create the 3D scene. In all these cases, these intermediate forms are then converted into the final 3D scene representations we've talked about, like neural radiance fields or 3D Gaussians. Alright, so after looking at methods that directly generate 3D structures, this next figure, figure 5, presents a different approach, image-based generation. This is interesting because it leverages powerful 2D image generators, especially when 3D data might be scarce. Part A of the figure shows what's called holistic generation. Here, an input like text or an existing image is fed into an image generator to create an entire scene image, often a 360-degree panorama, which is then processed into a 3D scene representation. Then, Part B illustrates iterative generation. In this method, an initial image is generated from the input, leading to a 3D scene representation. The system then renders a new view, which means it creates a 2D image from the current 3D scene as if seen from a different camera position. And this new rendered image, along with the original input, is fed back into the image generator to progressively extend and refine the scene. This iterative process helps build out more complex environments step by step. Okay, so building on that idea of using 2D data, this next figure, Figure 6, introduces video-based generation methods. Instead of just single images, these approaches leverage video generators to create 3D or even 4D scenes, which is great for capturing dynamic changes over time. Part A of the figure shows a two-stage method. Here, an initial input like text or an image first goes to a generator that might produce a single-view video or perhaps multiple static views. This output then feeds into a second generator, which creates a multi-view video. That's video from several different angles, and this multi-view video is finally used to construct the 3D scene representation. Then, Part B illustrates a one-stage approach. In this setup, inputs like text, an image, or even a bird's-eye view, which is a top-down perspective of the scene, along with action commands, go directly into a video generator. This generator produces either single or multi-view video, which then gets converted into the 3D scene. This one-stage process aims for a more unified generation. So from these video-based methods to all the other techniques we've touched on, it's evident 3D scene generation is a really dynamic field. This survey does a great job of bringing together these diverse approaches, highlighting how far we've come and the exciting challenges still ahead. It's a crucial resource for anyone looking to understand or contribute to this space. Well, that's our AI Research Roundup for today. Thanks for listening. I'm Alex.